Excellent. Shh. Oh. Give me a rest for 1 more minute. Similar. Threshold. I'm gonna die. Eating Korean food for 1 million years straight. Hello?
Hello, Chris. Hi, how are you? I'm fine.
Okay, all right, good. So holiday started for you, huh? Tomorrow, the evening of Chinese New Year. So we still
Yes.
do a lesson today, huh? Okay. So then let's just start. And we talk about waves, talked about quite a few properties of waves already. And we'll just continue. And okay, so what we start is a question, obviously related to the Doppler effect. And we assume that the plane's engine is emitting a constant noise at 120 hertz, or sound at constant 120 hertz frequency. And of course, it's flying away from an observer, say one on the ground, who looks at the plane and sees it going. So what we want to know is, of course, in the first question, what is the observed wavelength of the sound received by the observer? Very typical question.
So it's the observed velocity over uh, the actual frequency.
Okay, and what is the observed velocity?
330 plus 80.
Okay, all right. So plus Vs over the frequency. So we can say 330 plus 80 and over 120 hertz. Huh? So so we get 3 point. And what is that?
3.42
3.42 and unit of measurement
uh, meters.
meter. Huh? So it's just the frequency, the wavelength observed. Eh? And of course, question B is then, what is the observed frequency?
Um,
Going to talk about.
it's the normal velocity over observed wavelength.
Okay.
330 over 3.42.
Okay. So that gives us how much?
96.6.
96.6. Huh? Okay, hertz. Huh?
Yeah.
So in other words, what does the observer perceive in terms of hearing?
Uh, they
How
hear
does
a
it perceive the sound?
lower pitch.
Lower pitch, huh? Exactly. So, which tells us that if the pitch is lower, of course, it can. We can only know. We do not know when we look at the plane that it's at 120 hertz, obviously. So we have no reference measurement, so to speak. We just hear the plane as we hear it, but as it flies away. So what will happen? Will the is it Also, what I want to say is that's where I am, so where we are, and that's how the plane is coming and then passing by. So what happens to the say frequency?
We hear a higher pitch, and then sudden, when it goes over us, it becomes a lower frequency.
Okay.
No, no, no.
Huh?
Oh, wait.
Well,
Yeah,
because we
yeah,
talk
yeah.
about flying away, so no, you're absolutely correct. I know sometimes. So as it approaches us, so to speak, it goes up and then it goes down. So in other words, we would see something like from a higher point to a lower point, something like that, huh? Which of course is not zero here. just in a relative measurement point of view. Huh? Okay, so that, because the change is what we can observe as humans, right? Of course, with the measuring device, it's a totally different story. But as we have to basically need to have the situation of approaching and going away. Then we know as it comes closer, it goes higher. As it moves away, it will go lower. That's how we can somehow say it's not always so simple. Because let's maybe say the difference between 97 hertz and 120 hertz is not necessarily so much. Depends a bit on one's hearing. Huh? Okay, good. Then we go on to the next chapter, and that's about electromagnetic waves, right? And that part is a couple of things to be said. Not so many exercises. We come to that today still. So I would like to say lay the land, so the lay of the land. And before we go into, nope, I want to do it here, into some of the very obvious part, would like to cover some of the basic part. And it has an electromagnetic, so light, for example, is in the region of the electromagnetic spectrum. And at first, maybe people would not think that light has any connection with electricity, magnetism, and so on, right? Of course, for us, it's already difficult to say no, because we've already heard about that. But just from the outset of it is that, okay, this is an electromagnetic wave, maybe for something, and it's related to electricity and magnetism and waves. Huh? Because for us it's now very apparent, but for people in the past who studied that for a long time or various generations, it was not so obvious. What we see now was comparatively obvious. One of the key issues, of course, that the proceedings of electricity and magnetism made a big jump in the 19th century, which then led to the electric motor and the generator. And in between we had the steam engine. That was already a big step forward, actually. But the next one was the electric engine and the electric and the converter, I mean the power generator. That really made a huge jump then towards the end of the 19th, beginning of the 20th century. No? That's what we see today. The whole world is electrified, so to speak, apart from, of course, gasoline with combustion engines. And what we talk about is as well, that we know an electric current from the past has always a magnetic field, right? Very typical, a very simple picture. If that is a cross section of a wire, then we have around the electromagnetic field or the magnetic field around it. Where we know that, right? And on the other hand, we know as well, or that by and that means it's a moving particle. So this is just a simple way in a wire to have a moving particle, electrons. That's what it is. So you could have that in a much more complicated setup by having a free electron flying, like in a collider, for example, in those experiments they are doing nowadays, even with protons, where they accelerate these particles nearly to the speed of light and then let them crash into each other in order to figure out what are the Lego blocks, actually, of the universe. Not so long ago, that led to the detection of the quarks. So that means after we had the electrons, the protons, and the neutrons, it was realized actually they are made of other particles as well. That is generally known as the quarks, to make it the other way around. So that will be covered in a later chapter. So that means, on the other hand, we should never forget that a current is actually nothing else but a moving electron in a medium, if you want to say so, right? In that case, in a grid of protons and neutrons, and it can comparatively freely move through that. So the electron moves, and that creates then the magnetic field. Of course, what we know as well, or found out, is that a changing magnetic field, so this is a static magnetic field generated by the moving particle, but we could go the other way around and say, okay, I'm changing my magnetic field, I have it moving, pulsating, like the electron is moving, but the magnetic field is kind of moving, and that can induce actually a current in a nearby conductor. So that we know as well from the induction principles. So sometimes we just move the magnet, right? That's the most simple one, when we have the coil and we have the magnet moving back and forth, and that creates a current in the coil. That's called induction. Of course, there are various ways to generate such a moving magnetic field. And ultimately, as I say, today is a bit theory to some degree, that was ultimately by Mr. Faraday, who combined, they seem to be different theories. Electricity and magnetism seem to be something unrelated, kind of. But he developed then, the unifying theory, if you want to say so. Magnetism, of these two phenomena, which now became apparent they actually belong together. And later on, even further, that was then further extended by Mr. Maxwell. That's why we have the Maxwell equation these days, into mathematical equations especially. Faraday was a genius in experimental physics to a high degree, and Faraday was the one who could put that into, mathematical equations at the end of the day. So what he could do was that we can nowadays predict a changing electric or magnetic field, or if it has a change in an electric or in a magnetic field, it gives rise to a transverse wave traveling through space. Now that sounds a bit whatever, but it's just that we have either a changing magnetic field, so we saw that, right? Like moving the magnet inside the coil. Of course, the mechanism will be a bit different, but the same basic principle, and that can generate a wave, as a transverse wave, of course, traveling through space. And when he calculated all that, that ultimately became the speed of light. So the Maxwell equations on one side, and that led to the speed of light. So nothing comes from nothing, and everything is interdependent. So without Faraday, Maxwell, ultimately there would have been no Einstein, for example. Same as without Newton, same without Galilei. So it's a step by step in the end. And what he concluded, that he said light is a wave, and it's a vibration of electric and magnetic fields. That is something which we usually do not think, and it's not so important for us to do. We can't do calculations in tendency with that yet. That's a different level, but it's important to keep it in mind. And there's a nice illustration for that, just quickly, this one. So we have an electric, and you see it's a three-dimensional situation. We have a magnetic field, this one, and that varies, hence the fluctuation. That's important. Without fluctuation, nothing starts. It's like a principle. On the other hand, we have the electric field strength. So on this one, this height here, on this dimension, basically the z-axis, then of course it varies around this one. So height, and both change when traveling over distance. That's important. So that's basically what we know from a transversal wave anyway, that how it moves forward, and the movement is centripetal to the distance. And we see that, but it can not only be one dimension. That's what we usually look at. It can be a two-dimensional, because one is the electric field strength, and the other one is the magnetic field strength, which leads then to certain combinations, and the speed of the wave moving forward is ultimately the speed of light. C. That's what we typically call C. So this is basically, in comparatively simple terms, the bottom line result of Maxwell's findings, if you want to say so. So it's a combination of the variation of electric and magnetic field strength over distance, and hence over time, because distance is ultimately time. Different location in the space-time continuum, so to speak. So that leads then to much further investigations, to where we are nowadays here in the relativity of theories and so on. And now what we still miss, that's interesting to say. What we can say is Faraday had basically unified electricity and magnetism. Maxwell had unified electromagnetism, also basically you can say electromagnetism. So what we usually electromagnetism. So that is the phenomena of both these, what we just said, varying field strength and light, to combine them. And what is still missing, so, is the theory of everything, which combines everything, because we don't have that yet. We still have a breakdown of some of the theories. We have a breakdown between the Newtonian equations. We found a way, I mean, we means the smart people behind all that, but we as humankind, let's put it like that, that we can make a distinction when we say, okay, if we are in the bigger realm, in the macro space, we can basically use Newton mechanics, and when we go into micro space, we utilize, for example, Einstein's relativity theory. But it's like kind of two separate theories, and that of course bothers everybody, because they want to have one unifying theory to really explain everything with one set of equations, so to speak, not with the Newtonian approach and the Einstein approach, if you want to say so, because it goes about existence of particles of matter and so on and so on. And still, even that, what we now see with, let's say, Maxwell and Einstein's relativity, there's still borders where we can't explain certain things, and we find more and more of that even nowadays with better and better tools like the observatories. There are certain phenomena, like who would have thought that at the center of our galaxy is a black hole, right? That is something which is very, very new, and that is something natural. On the other hand, we know as well that about at least 3/4 or more of our universe is so-called dark matter. We can't explain it, we can't measure it, but we know it's there because it has a huge discrepancy between what we can observe and from other calculations what should be there. It's like, wow, it's not just 5 or 10% like error of calculation or observation. It's really something which is more dominant than what we can see and feel and touch, kind of, is there as whatever, like what it's being called for the time being dark matter, in absence of a better explanation. And so that is still missing. So that is still in this field of what still has to be developed and evolved. So we are a long way from having explained everything. Huh? But for us, we go back to Earth now, and we talk a bit about more the practical approach, orders of magnitude, and so on. And when they, of course, going still back in time a bit, that evolved further. So in between Maxwell and the theory of everything, there's still a lot of explorations and findings, of course. And one of them, of course, is, for example, the radio waves, like by Mr. Hertz. So that's why, of course, the frequencies are called after him. So they have a frequency that they vary, that these electromagnetic waves, like coming from Maxwell, that they actually move at different, I mean, they have different wavelengths, they have different frequencies. So there's a whole range of various different electromagnetic waves. That was a breakthrough on its own to identify that. And that led then very fast to practical applications, for example, like the radio waves. And nowadays, for example, we take it as granted that electricity is being transferred by cables. And we think, well, of course, this is the one way and the only way we can do it because it's dangerous. But if you really look at it, it's nothing else but an electromagnetic wave with a certain frequency and a certain amplitude, with a certain wavelength, and so on. So actually, we would not necessarily need to transfer the electricity, these waves, they are nothing else but specific type of waves, through a cable. We could as well send them through the air, like radio waves actually. And there was a concept for a long time in discussion, maybe 120 years ago plus, and that was basically Mr. Tesla, the one not behind the cars obviously, but behind massive inventions behind electromagnetism. And he was more of a proponent of sending electricity and and an Italian gentleman to send the waves through space, through air, which of course would have completely interfered with the radio waves. There would have been ways to do it in a safe way, just to say, but that's all now history. But just to keep an open mind, huh? What we sometimes have is not necessarily the only way. It's just one solution for many possibilities. Maybe it's the best, maybe not the best, but it's the one right now we have. On the other hand, by having confirmed, so to speak, the the electric waves, if you want to say so, to cables, which are shielded as well. We try to minimize the electromagnetic effect of the cables, like the high voltage cables, for example. So that now enables that we can send radio waves, which was for a long time the one way to communicate basically worldwide. But nowadays we go one step further. Now we are more into satellites and optic fiber cables in order to send data bits, zeros and ones, at the speed of light instead of actually modular waves, right? Before we really had all these waves going through the airwaves, so to speak, and they still do. And that is a good way now to look at the next part. Say, okay, what type of waves have we actually identified? And of course, you can have it in two ways. You can either go by wavelength or by frequency. Quite often we go by wavelength, like in this one, and we see the various types. Huh? And typically, of course, very clearly here, it's a very, very narrow range between the UV and the infrared where we see. So our sensory system is clearly adjusted to this one. That is an evolutionary step. We know from other creatures on planet Earth, they are more on the UV side, more on the IV side, infrared side, or some of them even on the, like bats, for example, ultrasound. So that's even then, of course, obviously not an electromagnetic wave, but a very different type of orientation. Okay, so that's important to keep in mind, and we see the magnitudes go from 10 to the power of 6 radio waves, so they can be, one period is extremely long. They have their own advantage. And of course, when we go to this side of the spectrum, then they have a very short wavelength. Now, as we can see, well, it depends on how we look at it, of course, but let's say the wavelength grows in that direction. So in which direction develops then the frequency? The magnitude by going positive, so to speak. This is a bit opposite, right? But this is, let's say, we say the plus side is here. So in which side does the frequency go?
Opposite.
Opposite, huh? Exactly right. I mean, it's exactly, huh? So frequency grows here. So that means we have those with very high frequency are clearly on this side. And what was later found out, that comes from Heisenberg, was then that the higher the frequency, the higher the energy content. That was another massive breakthrough, actually, which was very, very important for the theory of relativity, or to further develop that theory, actually. Huh? So nowadays, that's why we already learned that in GCSE, then these rays here on this side are more dangerous. Well, the reason behind is because the higher the frequency, the higher the energy content. That is very simple. That, of course, if assuming this is a particle still coming, the wave can be as well a particle. That's the dual side of waves and particles. And if that hits with that huge energy, of course, that's a very different situation. Look at the magnitude, right? The opposite as a 1 over it. This one compared to this one, this is like, wow. This is not like double or triple. This is like to the power of 10 multiple times. So they have a very, very high energy content, and that's why they are so dangerous, actually. That's why they, on the other hand, can penetrate certain materials. Comparatively obvious then, right? If you think about the energy they have, hence they have more force, kind of, in order to penetrate various materials. Important to remember as well, it's not so clean-cut like we usually see it. the boundaries are a bit fuzzy. So in this region here, we can be either an X-ray or no, an UV. Depends a bit on the aspect of how we look at it, but it's good enough for us to basically say certain cutoff regions, like indicated here. The overlap of the X-ray and the gamma rays, well, that is something we don't really have to bother with. That's for just the basic part to know which direction goes the energy. I always prefer that one because it goes together with the energy. This one, the frequency. But very typical, we talk about wavelength. And here it's just same thing we already know, just in the table. Same thing all over. And we see that radio waves here, or here actually, can have very different wavelengths. That has its pros and cons depending on what we want to achieve. Has to do as well with the ionosphere, so to speak, the one surrounding the Earth. There is an ionized part in our atmosphere, which of course interferes with them electromagnetic waves, right? You can imagine up here in the sky and then a wave comes, something like that. There must be something happening. And that is usually stronger in the evening. That means it has a certain reflection effect. So that's why then long-range radio waves are usually better transmitted at that time. And they can then, on the other hand, if you look at the length of that one, 10 to the power of 6, right? Can better deal with the curvature of the Earth, for example. So there's various ways. Or we know that the submarines, for example, it's then penetrating water and going to a certain depth of the water. That's another issue with the properties of a certain wave, which can therefore achieve certain targets we want to get. Okay so far, Chris?
Yeah.
Okay. All right. So now, there's not so much to be discussed further, actually. I mean, the basic relationship we know, we already discussed that before. That speed of light is the product of frequency times wavelength. So, which is an unbelievably powerful and important formula, and very simple, and yet kind of beautiful on its own. The product of frequency and wavelength. That is basically the bottom line we have to take out from this one. And now we can apply a bit of practical discussion, if you want to say so. So if we go and say, I have a wavelength of 1 kilometer, just a bit to give it some proportion. What type of wave is that? When we look at the various types of electromagnetic waves. What do you say, Chris? Radio wave, exactly. Huh? And what if it's 3 centimeters?
Also radio wave.
When you look at it, 3 centimeters, you would have to go into the negative, right?
Oh,
exactly, right? Because it's not to forget, it's all in meters. Huh? So with 3 centimeters, which range would we probably talk about?
Microwave.
Yeah. Okay. And what about if we talk about 5,000 nanometers?
Uh, 5 times 10 to the power negative 6.
Okay, that would give us give or take infrared, yeah. Okay, and if we go one notch short, 500 nanometer, what would we get then?
Five times 10 to power of negative 7. So visible light.
Yeah, exactly. I mean, this is just a simple game, right? Because the next one, of course, is then 50. nanometer, but it gives us a bit an idea of the dimensioning. Which one would that be?
5 times 10 to the power negative 8 is ultraviolet. Wait.
Yeah, the UV, right? Yeah, no, it's correct. It's good. It's good. So, I mean, it's about to give us an idea, right? So basically, we go by the power of 10 from each one, and this power of 10 gives us basically infrared, visible, ultraviolet. Huh? So along the lines of that one, together, of course, with the nano. That's for sure. Okay. And that's just to play around with this one. Then we can, of course, go as well into the frequency and go the other way around, just to familiarize us a bit with all that one. So when we say, for example, we have 200, typical, that with the frequencies, you have to be very careful, because usually that's not just expressed in hertz per se. It's just, it's, for example, like here, kilohertz. Huh? So that is something sometimes a bit tricky. Always to be very careful with the frequency. Which unit of measurement additionally to hertz, so the power, which one are we using? So when we talk about 200 kilohertz, what is that? What type of wave?
Speed of light divided by 200,000. 1.5 times 10 to the power of 3. So,
okay, so now of course it's as we have the table the other way around, we have to basically pre-translate a bit this one into what is which one in hertz, right? So to speak. But what would you say based upon that when you now look at it? Needs a bit more investigation. Radio wave. Okay. What if we go into, say, 100 megahertz? Megahertz.
It's just 3, so also radio wave.
Okay. Now, so there, you know, with the frequencies, we see really something. And if we, for example, take this one, 10 to the power of 14, because there we start to usually stop, just express it still in hertz, but with the power of 10. What do we get for that one? What type of wave?
6 times 10 to the power of negative 7. So it's visible light.
Visible light, huh? Exactly, visible light. Exactly. So when you look at it from a, but that's again, that's me. I think it's easier somehow to imagine the frequency than the wavelength. But again, that's what I think, because I'm more used to it. That's probably the way. The reason is when I see the 5 times 10 to the power of 14 hertz, that's a really massive kind of frequency already. And I have to say, wow, that's visible light. So we see from that point of view, it's really already in a very high frequency level, on a very high frequency level, just for the visible light. And when we go back here, it's not exactly halfway through. That would be somewhere, but it's around halfway through. Huh? So when you go halfway through, basically on a logarithmic scale with the power of 10, then we can say, okay, that's more or less in the middle, more or less, that's where the visible light is. Huh? So which means it's already very high on its own. And if we increase it not much more comparatively, if you compare it to the radio wave, and we go to something like 10 to the power of 18, what do we get then?
Three times 10 to the power of negative 10.
Okay.
So gamma or X-ray.
Yeah, exactly right. So we can go either X-ray or gamma ray. Gamma ray. Okay. So, and you see comparatively, okay, yes, it's 4 powers, 10 to the power of 4 difference, which on the other hand, when you look at the whole spectrum, is not so much. On the scale, yes, this one seems already a bit larger, but still 10 to the plus you to the power of 4. So, and then you already have such very, very, very different rays, like X-rays or gamma rays even. So, when we discuss that visible light, of course, it always means as well, we as humans, have the receptor in order to read those waves properly, right? So on one side, we have to receive the signal, so that we have the frequency range with that machinery, so to speak. They are, of course, not machines, but just to say, or that biological device, that organic device, which is capable of receiving those signals. And then, of course, we need a whole apparatus to transform that and ultimately create a picture so in our brain, which we then perceive as what we see. This is usually not really what people think about, maybe better, because it seems to be a very mechanical approach, right? We look around, see, well, let's call it the beauty of the world, but in the end, it's nothing else but rays being detected by our sensors and then transformed into a picture in our brain. I think this is too mechanical at the end of the day, but from a functional point of view, more or less that's how it works. So it's important to understand that. And there's as well, nowadays even more so, the link between, let's say, physics, math, and biology, chemistry. We see that especially when we think of artificial intelligence, right? If that's intelligent or not, but at least it's moving towards something which could at least pretend to be kind of a living creature, kind of something, even if it's not, certainly not now, but still. And of course, then exactly these questions come into play. How does such, let's call it AI, then interpret information or signals and make something out of it? And we see some results already, right, which are sometimes pretty stunning and in parallel a bit scary as well sometimes. Okay, moving on. So we said that we have these variations of the electric field strength and the magnetic field strength. And of course, they move perpendicular to the distance where we have the wave speed. That's something to keep in mind. We see that then a bit more in practical with the polarization. And did you have already anything to do with polarization, Chris?
Huh?
When we talk about polarization, have you already heard something about that before?
No.
Okay, in practical terms, maybe daily life, sunglasses, maybe.
Maybe making something that has a positive and negative end.
You see that sometimes,
Oh.
yeah, like with Polaroid, right? This is something which is actually a trademark. That is a certain surface and coating, which gives a better view, so to speak, in certain conditions of the light. I mean, that we see more. It's actually like a filter. And we are not recovering it a bit. They are at a later stage. I think it's with the waves. It will be in more detail explored how it really works. But here we get the first idea, and you can see unpolarized wave. It's actually very simple, kind of. It goes in all directions. It's just what we see, right? I mean, we have the sun, and wherever you are, or wherever we are, assuming the sun is stationary, kind of, and we travel with our Earth around the sun within a sun year, so to speak. And it doesn't matter where we are, we always have the sun light coming because of the tilt of the Earth. We have seasons. If we would have no tilt of the Earth axis, we would have no season. Just as a side remark, right? When you think of it, the Earth is slightly tilted like that, instead of, that's a 20 degree tilt. Actually, and that by going around the sun leads actually to the seasons and of course the opposite of in north and south as well. So, in other words, that's something we don't want to investigate, but just to comment. We always have sunlight, one way or the other, because it goes out in a 360, right, in a spheric way. And what we now can achieve, and we call that polarization. It's just a word which has been chosen to call it like that. And what you can see here is that this one, going through a slit, that's the kind of a very simple device. Of course, in its practical application, it has to be a bit achieved in a different way. But from an experimental point of view, you actually have a light source which is emitting, well, light in all directions. And of course, you have the wave coming. When you say, well, we have these various variations in different angles as well. So we said here, sorry, we said here we have these variations, these two, right? But of course, they vary in their angle, so it's not as simple as that they all have the 90-degree tilt. Some of it's a whole spectrum actually. That's part of why we have different frequencies ultimately, but that's not really important. So they move in various ways in the 3 dimension of X, Y, Z, so to speak. And if we now have a vertical slit, then we of course stop everything else. That's pretty obvious. So only that one, which is moving around, let's call that the x-axis, for example. It moves around the x-axis, also up and down in a y movement. And then it goes through the slit. Of course, the slit has to have a certain property in terms of length, for example, in order to let through certain waves. Otherwise, if the slit is too narrow, it will only let through some other smaller waves, those with lower amplitudes, and so on. But the basic principle is kind of simple. We let them through the slit, which means then the rest is filtered out. But from a practical point of view, we only get those through. And that's why we call that polarized wave. Huh? It has only a certain direction. And the rest is being stopped from a practical point of view. We see the others coming, which gives us a better view then under certain circumstances and depending on how these filters are really being made. So you can see on one side it must be a transverse wave, right? Otherwise, of course, it doesn't work. And that's why ultimately, of course, any electromagnetic wave can be polarized. It really just depends on the plane, the one we choose, right? So that's why I say in practical application, as we have so many different waves coming, it's for us to choose which ones we want to take through, positively speaking, or let through, and which ones we want to keep back. So that, of course, needs further investigation so that we know, for example, okay, which filter should I apply in order to, for example, I'm looking at water, assuming clear water, but the sun is shining onto the surface, so something like that. There's various waves still, it has a spectrum, red, green, blue, and then the water is clear, so there's something, say, fish swimming underneath the surface of the water, but due to the reflection, I can't see them really. If I apply the proper filter, I can actually see what's swimming in the water. That's the very, well, kind of, at that time, many years ago, surprising effect of the Polaroid, that you have these sunglasses on. With the normal sunglasses before, they just kept back the some of the UV, gave you some shade, etc. But now with those, there was an additional effect of filtering, not just make it not so bright for you, protect the eyes, etc. There was the additional effect of, oh wow, I see more. I can look at the sky. The sky has different shades of blue, for example, because it's not so let's say, overshone by the very bright light, and it's not just darker, it's just really different shades of blue I can start to see. So that is really a question of how I choose my filter. Huh? So far, so good?
Yeah.
because there's some later on we will go more into the details of calculation. Not today. That's more for the later chapters when we talk about waves in more detail. This is just a bit like an appetizer kind of. And again, same thing. So how we can achieve that? A little bit of a hint. There's some molecules, long chain of molecules. So obviously we can operate with long chains of molecules, which we use for that coating, which then have this polarizing effect. And that then the plain polarized light comes through like this. Basically nothing else but what you already said here, but in terms of a practical application of how we can actually achieve that. So you see the link then to chemistry, for example, or physical chemistry, physics, in order to get such effects being made by the behavior of these molecules or the impact they have of the wavelength and the polarization or the filtration and the passing through of certain rays. That's a more general way to say it. Huh? So it has a very unique, we call that the axis of transmission, like what it lets through. So you could imagine here that if you start to tilt it, that you probably have a different, sorry, that was wrong. So if you start to tilt that one, the axis, if you start to tilt it, you will have a different effect. Because all 360s are included here, so if you start to tilt, something else will pass through and the others will fall out. And of course you can start to combine it to some degree, but that's then the higher level of how to achieve near perfect sunglasses, for example. But we just need to know a bit the basics. The axis is an important one, how it behaves compared to the direction of travel, which we already know. But it's not just the 90 degree which is of importance, there may be others. And this one shows it a bit. And what happens with the two situations, right? So you see here the Polaroid, also the filter. We can as well call it the filter or the Polaroid. And they have the analyzer of what's coming through. And you can see here that depending on how you then have the analyzer, of course you can change as well the Polaroid, but it's easier to change the analyzer. Change its axis, so it has now a 90 degree axis compared to the Polaroid. And that means the ones it lets through, of course, can't go through here anymore. And that's the most obvious and most simple way to explain that we say, well, we actually talk about like both have a slit. That makes it quite simple. Of course, if I now turn the one here, which has that slit, but now I make it as such, of course. So of course, those which went through before this one, of course, will not go through anymore because it's a totally different property, or in other words, the slit changes from, if you look at it from let's say this angle, from the slit was like this, and now of course it's only like this. So we have this situation, right? Hence, with the same filter as before, it will stop and it will not let it through. Kind of very simple, straightforward. To achieve that in reality, of course, makes it a bit more difficult. And when we look at the practical, and of course you have between that, so basically you vary that between 90 or 0 and 90 degrees, right? So this is the 90 degree. Of course you can imagine you can choose anything in between to get certain effects. And I think one of those, which is when you have a Polaroid with the vertical one, like the one we just have here, that reduces the glare of reflected light. I mean, we won't investigate that in more detail in order to prove it, but we can memorize it. So this is the most obvious one. The glare of light. So that is exactly what happens when you look at surfaces like water. There's a massive glare, or snow for that same effect, but we can't see underneath the snow. But with water we can then, so it becomes translucent, so we can see through the water. Otherwise the glare prevents us to see through the surface of the water. with that Polaroid in place and the 90 degree, also I mean the 0 degree of course, sorry, still the same slit here, then it eliminates a lot of that glare, which is that's kind of chaotic frequencies as a part of the reflection, filters them, so to speak, out. What it means in very simple terms, actually, it just lets through what we want to see, and what we don't want to see, it holds back. It's actually a comparatively simple principle, but it needs quite some basic know-how about how waves work and all in order to come up with such a simple solution. Huh? So that's pretty genius, actually, to come from one basic principle, okay, how waves behave, to something like such kind of an application. And that is quite often actually how it happened in the past, that they were investigating basic effects. How does that work? What about the magnetism? What about electricity, etc.? And suddenly they realized, wow, there's something I can use it for. Like, okay, if I can induce a wave, I can induce electricity. If I move the magnet, I have a generator. Out of nothing, kind of, I can generate electricity. Fantastic, right? You need, of course, for example, a moving part, which is what we usually have in a generator. And then, of course, the magnet, and then we have the copper coil, blah, blah. But based from the basic experiments of what is going on, they suddenly realized what they can really do with it. And it's not that they were in search of per se, oh, how can I make electricity? That was not the driving force. It was the other way around. What is going on, the basic principles, and out of that, kind of by kind of coincident, accident sometimes, they figured out what they can really do in practical terms. And then, of course, at some point, they really started to investigate what else can we do with all that, huh? Like, but it always needs a base. The Polaroid is a good example. It started somewhere and it came to this one. Reduce the glare of light. Huh? Okay, now important as a last part of here, because that's something we can apply and we will apply in our calculations a bit, is this so-called law of Malus. That deals with the polarized light incident at the Polaroid. No? So we see very clearly. Now we go a bit into calculations. Our Polaroid, and then it depends on how we tilt it. So, as it so nicely said, the transmission axis of the Polaroid is at an angle theta to the plane of the incident light. Huh? Makes a lot of sense. That is what we actually talk about here. This is the angle. So when the angle is 0, also it's straight up, like what is shown here, no tilt, then the light will go through the Polaroid. And when the angle is 90 degrees, there's no light transmitted. It makes kind of perfect sense because we start to tilt it. Huh? So important to remember, we tilt it like that. And then, hence, the more we tilt it, the more different will be what's coming through. And that goes then, as this is the cos of that angle actually, so we can say, well, it will go through with that's some further investigation we are not doing. We just take it as granted, goes with the square of the cos. Huh? So the original intensity times the square of the cos of the angle. Clearly, if the angle is 0, we get the max. That's why for such kind of investigations, very often it's then the cos, even if you usually look at the waves with the sine curve, right? But the effect is usually with the cos in many cases. And in this case, it's even with the square. So that means it's a diminishing effect, right? Non-linear, actually. So the moment we have the cos going below 1, which it will, so then we don't have, let's say, 0.9. We will not have 0.9 times the original. We will have 0.81 because it goes by the square. Huh? So it will go rapidly down. So it will be one of those typical curves. Huh? Otherwise, it would go down linear. That would be if it would be without the cos. Just to make that quickly. That would be just how it could go on the cos. And with cos square ups, that's a bit no. And if we cos square, it will go something like that. Huh? Being because cos is always, because cos is less than 1. Huh? Otherwise, it would be a different effect. Huh? So this is something we should keep in mind. And in other words, what we can say, just to write it down, so the intensity I get is the result of the original intensity times the square of the cos of the angle of the Polaroid. Huh? Or the incident angle, so to speak, between the Polaroid and the incident. And that's what we call Marlow's law. That has quite some impact then as well in practical applications, as we can imagine. So, and we can see that is indicated now here. The intensity will of course vary, and the picture itself will not necessarily be so different to what we observe. So of course there's no change between at 0 it's at max and at 90 degrees it's at min, and the curve looked kind of normal of what we would expect from a cosine curve, but we just have to keep in mind that it of course varies with the square of the cos nevertheless. Is that clear, Chris?
Yeah.
So basically, in other words, it's a cosine squared graph, right? But it's well, you can't really tell from the graph itself actually, because of the intensity with the I0, how it will develop accordingly, the intensity accordingly. Huh? Okay, so maybe to have a brief question, just a qualitative one. When we have unpolarized light, I mean just normal light, so to speak, but we quite often refer in that context as unpolarized light. Right? And it hits a Polaroid, or its incident at a Polaroid. What happens in a few words?
The only part of the amplitude can go through.
Yeah. Yeah.
At 90 degrees angle.
For example, yeah. It depends on how you, of course, design the whole thing, but yet the plane polarizes it exactly. Yeah. So that means or in more technical terms, actually the electric field vibrations along the transmission, only those will go through which can pass through that plane accordingly. Huh? We have this kind of slit, so to speak, or which only let them pass. All other oscillation from the unpolarized light, also from the source, will be blocked. They will be blocked. And if it's about then, okay, how would you achieve that? Then we can talk about these long chains of molecules. Huh? That is, they act, and of course they like you said, they are arranged as such that they are not letting it through. So they are like we saw before. Let's go back to this one. So here the long chains of molecules, the Polaroid is plane, and hence only those waves which can pass through this arrangement of these molecules can go through. So when you think of those who are not going through, what may happen to some of that? I mean, what could, in tendency, what could you observe if you would look at this Polaroid filter? When you think that all the waves are hitting it, but only one comes through, the rest is being blocked. So we talk about energy. So what may happen on the filter to some degree at least?
Maybe it's increasing in temperature.
Yeah, very good, exactly right. So we see a very classical situation of this light energy, so which is then another proof, by the way, on the side that light has energy, right? Just to say, from such a observation that we can say, well, why is it warming up? Of course, we all know if we expose a piece of metal to the sunlight, it warms up. Okay. We therefore have to say light must have some energy, but some may then argue, well, that's the infrared part, for example, of the light. But just to say, because the sunlight contains a whole range of waves. But whereas if we do that experiment here, we clearly only talk about light waves, and henceforth it shows that even light on its own transfers energy, so it doesn't need the so-called heat wave, the infrared, which is the typical heat wave usually, as we call it, is then the one which is containing energy as well. Huh? Okay. Other question, when we look at the a plane, the intensity is 12. And intensity, not to forget, what is the measurement unit of intensity?
Power over area.
Okay, all right. Okay. Huh? All right. So, henceforth, when we now say we have something, we have a 45 angle degrees. What is the intensity of the transmitted light? So, of course, this we will call then intensity 0. So, what is the transmitted intensity?
Times cosine squared 45.
Okay. And how much is that? Six, eh? Oh, 3 watt, eh? Exactly. So another, just 15 degrees more, in other words. So when we look at this one, and say 45 degrees, 60 degrees, so this is 45, and here we go by another 15, plus 15 degrees, and we go from half to half, huh? So that was 100, so to speak. This is 50, in other words, and this is 25. Huh?
Does the 60 degrees start from the vertical or the horizontal?
My bad. Yeah, of course. I mean, you will measure it from the horizontal. That's correct. This is just more to indicate how the angle grows, right? But it's a good question. You can put it both ways. The one I choose is just the traditional one that I say it goes. This is the direction of the growth of the angle. But of course, like you said, basically we look at it from this one. But you know what I mean, right? Because you can look at it both ways. It doesn't matter as long as you say, oh, this is the plus direction, so it increases the angle, and the higher the angle, the less the intensity. In practical terms, I just have to be clear how is my angle defined. That's then another story. So, like we said, this is theta here. So, of course, I could tilt if I want to, I could tilt my show here and say, well, it goes this way. But we don't usually do that, right? So I could tilt it all over and say, this is the growth of the theta angle. This is then more practical, in line with my basic setup, but it doesn't have to be like that. And that's quite often the case it's a good remark from you, Chris, that yes, the angle may be like this, like what we see here, but the display is just following the standard procedure where we go typically from 0 here to 90 here to 180 there, because this is typically the agreement of how we show angles. The key here is only that I clearly say this is the growing plus, so hence I'm correct. But if I want to be in line with how my setup is, then of course I can choose that one as well, which is then more obvious, more telltale. This is more telltale. This is more in line with my standard way of showing how angles grow and what happens to the values accordingly. Okay, good. And then, well, we can go into some questions. Now we move away a bit, repeat a bit what we had in the whole chapter actually from A to Z with a couple of selected questions. And I would like to do this one. It has to do with the Doppler effect, obviously. And we would like to do some exercise now first again with the Doppler effect. Huh? So first of all, just a brief explanation in words, qualitative. Why is the pitch of the siren changing?
Because it is leaving and approaching the student.
Okay.
So the observed speed and therefore frequency is changed.
Okay, so what you say is that I have the source is moving, the source of the sound is moving. So apart from emitting the sound, which has its own velocity, it will either add or subtract additional velocity because the source is moving. Huh? And that in consequence has an impact on the of the observed frequency ultimately, because it either then adds or distracts that additional, that delta may be plus or minus, of course, that additional velocity, that of the moving source, accordingly. So that we have, and that is then the ratio, right? What we always say between the situation with or without, so to speak. Huh? Okay. So when we go into question B now, what are the max and the min frequencies that the student will hear?
Maximum frequency is when the boat is moving directly at the student.
Okay. Okay, and I calculated. What does that mean?
So it's the source frequency times 330 over 330 minus 25.
Okay, yep. Good one, huh? So 305, huh? So that's why it's nice to think of the ratio, right? This is exact. So we always, of course, the frequency is given. That's the source, so that will not change. But it will be influenced, like we discussed it before, and then either by coming towards it or moving away. Huh? And coming towards it means it reduces the relative velocity. So hence, the factor here becomes greater. Hence, the max, it will be max. It will be increase actually. Or when we go the other way around now, how do I have to describe the situation then, Chris?
The boat is moving directly away from the student.
Yeah, right. So that's so kind of, so the student. Now, not that the student moves towards it. So that's a bit, but it's like more like that. So the boat is passing by, huh? Because the student is in a fixed position. Okay. And henceforth, what do we get? How is our ratio changing?
Bottom is 330 plus 25.
Yeah, exactly. Yeah? So it goes up, hence frequency goes down. Exactly. And if you calculate it quickly, I'll do that myself because they have a clear mistake. 330 divided by 305 gives 1.08 roughly times 420 makes 454. 454 hertz, and the other one is 330 divided by 355, that's 0.93 times 420 gives 390. Yeah? Okay, so in tendency that should be quite a substantial difference in pitch, which is probably from really most people easily to recognize. Huh? Okay, so the question C we already answered actually. That was part of what you said already. Okay. Now, still a bit along the issue of the Doppler effect. We have some air particles as a sound wave passes. And the position of the air particles. So they are obviously, if you look at it properly, not equally allocated. Something must go on. And of course, the question comes to it and says, show the region of the wave where there's a compression situation. And where do we have compression situations, Chris?
Where the particles are denser.
Okay, yep. So, I mean, that's now, of course, difficult to do that remote. So we would have something here, right? We would have something here as well, where we have compression areas. Huh? Okay. The opposite, where we have the rarefaction.
The part where the particles are away from each other.
Yeah, right. Huh? So we have something like here, for example, or here as well. Of course, there are the portions as well. Just a region is okay. So how the particle moves, also the 1p, this one, how does it move as the wave passes? What is the movement of that p when we look at how this wave is behaving with these compressed and stretched parts?
It does not move.
Will it? As the wave passes, huh? So that's important. So as the wave passes through. So the key question is always in which direction, right? You have two different types of waves. So which one will it be when you look at this one, at the pattern?
Oh, actually, it moves left and then
Okay.
right and then left.
Okay, exactly. Okay, yeah, good one, exactly right. So this is important. This is an important part, absolutely. So first of all, it vibrates. We can always say that. That's a sure. I mean, we would not have a wave without a vibration, actually. So that's part of the answer. Also, it seems a bit silly. And of course, like you said, there's various ways to say it, which is fine, parallel to the direction. Huh? For example, of the oscillation. So that would be one way, or the way you say is absolutely correct. Huh? So it moves along, so to speak. Okay. And now the sound wave has a frequency of 240 hertz. All right. Okay, let's jot that down. 240 hertz. In terms of the movement of an individual particle, what does that really mean?
it moves and goes back to its original position 240 times a second.
Okay, yeah, all right. So we can say that. So it moves back and forth, right? Moves back and forth. So in that sense, it has max and min positions. Max, min positions. And of course, an equilibrium as well. Around, we can say around an equilibrium position. That's what we then always see when we look at the wave like that. And you can say, oh, this is actually the equilibrium in between. And then, of course, and it moves then. And then it moves. That's like 3 star. And then it moves 240 times per second. Huh? So it does that. So a complete move is done 240 times. So from that min max, starting max, min, go back to the equilibrium, so to speak. Like we say, we can always choose any point. We can go from max to max or whatever, min to min. That doesn't matter, but it has to be a complete cycle. Huh? And it does that 240 times. So I think this is a very practical, it's a good question. And to keep in mind what really happens with a wave. It's nothing really magic, it's just a simple movement. The way we show it then, typically like this, is then something like, okay, so, oops, that was not like I wanted to do it. Right, no, still not. Something like that. Huh? So that's what we say, this is nothing else but the movement over time, for example, or over distance. It depends. Huh? Depends on what we are choosing. Exactly. And that's why, of course, it has any position as we move along, and hence we in the end get like a curve. So as we plot the position of and that's a very typical, I like that one, that's where everything always falls into place. You have nothing else but the yx or an xy plane, and you say nothing more about then where is that particle positioned, for example. Either as it moves, so x could be time, distance, or could be time. Then you say it is stationary, but it moves up and down in its position, so that's simply the up and down movement in the y. And if t is x is t, then it's nothing else but the snapshots. The particle does not move forward, right? It doesn't move forward here, but it moves up and down over time. And if I do that, plot that in that xy axis, then I get that sine or cosine curve accordingly. Okay. Now, when the wave has the speed of sound, 320 meters, so what is the wavelength?
(320 divided by 240).
Okay, yeah. So we get something like 1.3.
Yeah.
1.3 meters. Huh? Okay, so what we can say is if that wave, and we see, okay, it moves at the 300, so at the speed of sound. So the question becomes then obviously very much so, at what frequency does it vibrate ultimately? So how many times does the wave happen, so to speak, per second? And that, of course, defines then how long the wave is. So 1.3 meters is actually already a pretty long wave comparatively, right, when we look at the whole spectrum. Of course, here they're dealing not with electromagnetic waves, but with sound waves, but still. So, whereas if I would like to shorten the wavelength, then of course I have to increase the frequency. It's obviously very obvious in that context. Huh? All right. Okay, one more with the Doppler effect. But I like this one because it's a bit of a practical application of what we can do with the Doppler effect, in this case in a medical device. So I just let you read it through. Huh?
frequency received should be lower.
Okay, very good. Oh, all right. And why is that?
Because the particles in the blood are moving away.
Okay, yep. So something very basic, so like we know it now from the Doppler effect, huh? Applied in a very interesting device, but moving utilizing that basic Doppler effect, but then translating that into a technical device for a medical purpose. Okay, so that explains number 2 actually, A2. And what are the differences between the frequency emitted and the moving particles of the emitted by the moving particles and the frequency measured by the detector?
Frequency measured should be 4,000 times 1,500 divided by 1,530.
Okay, yep, B and C. Okay, and I make that 1,500 plus 30. And what do I get in result?
400,
That should be.
4,400.
Sorry, that one should be, of course, 4, right?
Oh.
Right or
4 million.
so which unit of course it depends on what are we taking, right? So centimeters per second.
Just
So
use 4.
we can leave it with okay.
So 3.92 megahertz.
Exactly. Huh? 3.92 megahertz, right? So this is a good exercise in terms of that we can neglect as in some parts certain units, right? So it makes our life easier and just keep it like it is with the mega, for example. Okay. And what is therefore the shift in frequency? Because
4
we want to
minus
calculate yo, huh?
0.0784.
0.0784 megahertz. Huh? Okay, so that's if we translate that into no mega involved, what would that be? Just hertz? Gives us maybe a better understanding of what we're talking about.
78,400.
Yep, exactly. Right. It gives us a bit more. It's a bit more tangible, I think, in Tencent because we know our hearing is around 20 up to 20,000. So we know, okay, wow, that's quite significantly above that one. Gives us a bit an idea, right? Megahertz. Well, over time, of course, if you are more engaged in certain applications, where we always talk about megahertz, for example. That's why quite often this is then referred to eventually as the energy intensive area of electricity we're discussing, stuff like that. Huh? Okay, all right. And last but not least, what about C?
Because the particles are moving away from the source of the sound.
Yep.
So there is still a relative speed.
Yes, exactly. Huh? So very good. Yep, exactly. Yes. So that shows that sometimes it's then a bit more complicated, right? So where we then have to do some compensation calculation to get the final result, actually, which you can use, for example, in the medical device to get the true result, so to speak. Huh? Okay, good. Let me just see. Yeah, I think we covered that all for today. You've seen there's a couple of what like said, the papers from last time, and I will see that I have some questions covering the subject of today. So I will send that to you as well eventually. But you could just go ahead like you want, right? We have the two papers. I have one third one I will send later on again. A lot of the questions we have answered, but it's well for your own reference. And some of the questions we didn't deal with, so you may do them. And I try to see that I can send you something regarding what we covered now with the waves in chapter 12, huh? So that you can do some work on that one. And we'll do some of the questions too next time as well. Apart from that, like I said, deal with a couple of questions next time related to the whole chapter 12, apart from sending to you some upfront. We will then continue. Is it okay, Chris, to go into chapter 13 then at some point next time?
Yeah.
With the so-called superposition of waves, huh?
Oh, okay.
That's where then we see the typical diffraction effects and so on. So where to some degree polarization is like a subchapter of that one ultimately. Okay, all right then. Have a nice happy new year start and see you in the new year. Huh?
Yeah. See you.
Okay, thank you. Bye.
Oh my god. Oh my god. Oh my god. Travis Scott. Is that a Big Mac? $3 a.m.
It's 3 a.m. Let's eat at a convenience store in Korea.
That's loud. It's only
It's 3 a.m.
Dude, ramen looks so good, man. Why do people don't like it?
$6.
$6, 5 lives.
Okay, so I just actually finished this Ford. What do you guys think? I know I just blocked out the country.
Dogger bogger. How do I know if I'm a pogger or a dogger? Viff. Wow. Very important Frogger.